This is your presenter, Asloob Mudassar, and I am presenting slide number 10 of the course on atomic and molecular physics. The topics that will be covered in the 2 days lecture are radial wave function in a central potential of hydrogen atom, plots of radial wave functions, and radial probability density, full wave function of hydrogen atom, and 3D visualization. Quantum mechanics of hydrogen atom. Radial wave function in a central field. Here I assume that the electron is in a centrally symmetric potential denoted by V of R and that the potential vanishes at infinity. The radial part of the Schrödinger wave equation following equation 9.12 is given by. This is the equation which we have labeled as a 10.1 equation. This equation for the first time was cited as equation number 12 in slide number 9. So let me read this radial wave equation: minus h bar square over 2m naught, then 1 over r square partial derivative with respect to r of the term within the parenthesis is r square times partial derivative of r with respect to r plus v of r plus h bar square into times omega l divided by 2m naught r square, and this bracket is operating on the radial wave function capital R as a function of r, and then on the right hand side we have energy, total energy of the system multiplied by the radial wave function capital R. From equation number 9.39, which we have discussed in slide number 9, the following relationship can be written. That is omega L, because you see that omega L in equation number 10.1 is was unknown, and it was found in the lecture number 9. The value of omega L was found, which we are slightly reproducing over here. So from equation number 9.39, we had the relation omega L is equal to m max multiplied by m max plus 1 is equal to m minimum times m minimum minus 1, where m max is the maximum value of the magnetic quantum number m and m minimum is the minimum value of the magnetic quantum number m. And you see that there we set that the m max is equal to plus L and m minimum is equal to minus L. So equation number 10.2 reduces to omega L is equal to L times L plus 1. So this is the value of omega L, and we can substitute the value of omega L. That is, we can use equation number 10.3 into equation number 10.1, and the resulting equation that we get is over here. So you see that there we have replaced omega L by its value, which is omega L is equal to L into L plus 1. This is shown over here in equation number 10.4. And we have to solve this equation so that we can find the radial wave function of the hydrogen atom. Now you see that we have the derivatives there in the radial wave equation. For example, in equation number 4, you can see that these are the derivatives: 1 over r square times a partial derivative with respect to r of the terms within the parenthesis which contains r square times a partial derivative with respect to r. So let's simplify these derivatives, and the simplification is shown over here. That is 1 over r square, and the partial derivative with respect to r of the term within the parenthesis is r square times a partial derivative of r. This is equal to, we have written that derivatives in terms of the exact differential, that is the d square over dr square plus 2 over r times d over dr. So we can substitute this derivative in equation number 10.4, and the final relation that we get is this: d square over dr square plus 2 over r times d capital R over dr plus, within the parentheses we have a minus v prime as a function of r minus L into L plus 1 over r square, and this whole bracket, square bracket, is multiplied by capital R, the radial wave function of the hydrogen atom, divided, and that is equal to 0. And you see that in the writing equation number 10.5 from using equation number 10.4, we have introduced these derivatives, and we have also introduced equation number 6 and 7 in order to write equation number 5. And equation number 6 is A is equal to 2m0 over h bar square times capital E, and this will be equal to minus kappa square when the energy is less than 0, and it will be equal to k square when the energy of the system is greater than 0. For a bound state, which is the state for the case of the hydrogen atom where the electron is bound to the nucleus, and that forms a bound state system, for that system we shall take E will be less than equal to 0. So mainly our emphasis will be equal to on the energy of the system where the energy is less than 0, that is the binding energy of the electron, which is negative, which is taken as negative. And you see that in the writing equation, in order to write equation number 10.5, we have divided equation number 10.4 by the term minus 2 times m naught divided by h bar square. And then we have introduced these parameters, that is, we have introduced the parameter A, and also we have introduced V prime as a function of R, which is equal to 2m naught over h bar square times V of R. And this is equation number 7. So we have introduced equation number 6 and equation number 7 in writing equation number 5. Assuming that R of R, that is capital R, must vanish at very large distances R using the substitution. You know that R is the radial function of the hydrogen atom. So when the electron is farther away from the nucleus, that is, it is ionized, it has left the nucleus, then you see that R must, capital R, that is the wave function, must vanish for large values of R. Because when R will vanish, it means that the electron is not existing within the nucleus. So here we are assuming the condition that capital R as a function of R must vanish for large value of R. And that explicitly can be represented by equation number 10.8, that is capital R as a function of R is equal to U of R divided by R. And you see that on the right hand side, it is obvious that when R will increase, then of course the radial wave function capital R will reduce in its magnitude, and ultimately for a very large value of R, the capital R will go to 0. So that is why we have made this explicit substitution that capital R can be represented as U divided by R, where U is also a part of is also a R dependent wave function, and this is shown in equation 10.8. Now you see that we need to calculate the derivatives. For example, in order to solve equation number 10.5, we have to calculate two derivatives. One is shown in green, that is 2 over R times dr over d, capital D derivative of capital R with respect to dr, and also d square, that is the second derivative of capital R with respect to R. So we have to calculate these derivatives shown in green and red using the capital R defined in equation number 8. So the first derivative is 2 over R, the derivative of the term 2 over R times derivative of capital R with respect to dr is equal to, is shown on the right hand side, and the simplified version is shown as shown in equation number 9. And these derivatives are simple to follow, so I am not going to explain them. Now the second derivative is d square capital R over dr square can be split into d over dr and also d capital R over dr, and we have already calculated this derivative shown in blue, and I have shown that value of that derivative in blue on the right hand side within the parenthesis. And now I am further, once again I am taking the derivative with respect to R, and that is shown in equation number 10. So using equation number 9, that is this equation, and also using equation number 10 into equation number 5, where equation number 5 is this. So using these derivatives calculated from equation number 8 and substituting these derivatives, that is using equation number 9 and also using equation number 10 into equation number 5, the equation number 5 takes the following form, that is d square U divided over dr square plus within the square bracket we have a minus v of r, v prime of r minus l into l plus 1 times l times l plus 1 divided by r square, and then we have u as a function of r, and this is equal to 0 as shown in equation number 11. So you see that now we have transformed equation number given in equation number 5 in terms of the capital R as the radial wave function. We have expressed this equation number 5 in a more simplified form using equation number 8, and the equation number has been expressed in terms of the wave function u of R. Now you see that we are going to apply some conditions over here so that we can simplify this equation. So equation number 11 can be simplified under the assumptions that when r goes to infinity, that when r is very large, then of course the term which is L into L plus 1 divided by r square will go to 0, and also the potential which is V prime of r will also goes to 0. Because the V prime, the potential V prime of r, you see that is defined in equation number 7, and it is in terms of the V of R, and since V of R is a central potential, that is it depends upon 1 over R, so it means that when R will increase, V of R will go to 0, and ultimately V prime of R will also go to 0. And this is what I have shown in the assumptions, that under the assumption that R goes to 0, the third term within the bracket and the second term which is a potential V prime of R will go to 0, and then only the first term which is capital A will survive. Now you see that we are going to discuss the condition when energy is greater than 0. So you see that we have defined the energy over here in equation number 6, that is A is equal to 2m0 over h bar square times E, and you see that this is whole as defined as minus kappa square and is equal to k square depending upon energy is less than 0 or energy is greater than 0. So A and E are directly related through these constant 2m0 over h bar square. So I am going to solve the case of energy E greater than 0, and of course when E is greater than 0, it means that the constant A is also greater than 0. So if we assume that A is greater than 0 in equation number 11, with V of R, V prime of R is not present, and the third term which is L into L plus 1 divided by R square is also not present, only capital A is present within the square bracket, then the solution of equation number 11 can be written as shown in equation number 13. That is U of R is equal to C1 into e to the power iota kr plus C2 into e to the power minus iota kr. And you see that both solutions, these are actually the linear combination of the solution. The individual solutions are e to the power iota kr, and the second individual solution is e to the power minus iota kr, because these two individual solutions satisfy equation number 11, and we have written equation number 13 in the form of the linear combination of the two solutions by choosing arbitrary constants C1 and C2. So U, that is the solution U of R, that is the solution of equation number 11, is equal to C1 times the first solution plus C2 times the second solution. And you see that in terms of the capital R, which is actually the solution we are looking for, so capital R will be equal to 1 over R times U, and U is written in the parentheses. So capital R is defined, is given in equation number 14, and U is given in equation number 13. Now we can analyze the equation number 14 a bit. The result in equation number 14 is obtained due to the time-independent Schrödinger wave equation. Because the Schrödinger wave equation that we have written was time-independent. Instead of time, if time-dependent Schrödinger equation is used, then a time dependence factor e to the power minus iota omega t would appear in the solution, and the two solutions would look like as given below. So you see that this additional term which I am shown, which has been shown in the red e to the power minus iota omega t will appear if we are using a time dependent equation. So if so, the solution in equation number 13 and can be written including the time dependence, which is given in equation number 15. So capital R as a function of R is equal to 1 over R. And now we have written as if we have solved the time dependent Schrodinger equation. That is, we have incorporated the time dependence over here, which is the factor e to the power minus iota omega t. So we have C1 times e to the power iota, and within the parentheses we have kr minus omega t, plus the second solution C2 times e to the power minus iota, and within the parentheses we have kr plus omega t. So you see that in the red, the phase factor is kr minus omega t, and in the green solution we have kr plus omega t, because equation number 15 gives you the linear combination of the sum of the two solutions shown in red and green respectively. The solution in the red represents a spherical wave propagating outward, that is away from the nucleus, and the solution in green represents a spherical wave propagating inward, that is propagating towards the nucleus. Because the phase factor is constant in both cases, that is kr minus omega t is equal to constant. Similarly, for the green part, kr plus omega t is equal to constant. These two constants could be different. So kr minus omega t is equal to constant, and kr plus omega t is equal to constant. So we have written these phase factors to be constant for the red wave, for the red solution, and for the solution shown in green. So you see that as these parameters, these phase factors are constant, so as the time lapses, R should increase, whereas R should decrease. That is, when the constant shown in the red will increase, then in order to keep this the term on the left hand side to be equal to constant, R must, when the time will increase, that minus omega t will of course decrease, because there is a negative sign with that one, but time will increase, minus omega t will decrease. So in order to compensate this decrease, R must increase. So when R will increase, then kr will increase, and kr minus omega t should remain constant. So as the time lapses, then R should increase. But what consider now the green function, if time increase, then omega t will increase. So in order to compensate this increase, R in the green function must decrease, so that kr should can compensate the increase on omega t, and the term and the phase factor remains constant. So the phase factor has to be constant for both the solution written in red and the solution written in green. For the solution in the red, of course, the R will increase, and for the solution in written in green, the R will decrease. So as the time lapses, the R shown in red should increase, whereas the R shown in green should decrease. Thus, the wave would propagate outward and inward. Now you see that when in the classical Kepler problems, a hyperbolic orbit corresponds to a spherical wave coming in from infinity. So you see that if a wave function is generated, and if a wave is propagating and is coming from infinity with a hyperbolic, will have a hyperbolic orbit, and that is equivalent to the case when the spherical wave is coming from infinity. And if the spherical wave is emanating from a point source and is moving away towards infinity, then we can treat it as a spherically diverging wavefront. And in both cases, the orbit will be hyperbolic orbit. So you see that when the stellar objects comes towards another stellar object, the orbit they follow is usually hyperbolic orbit, and it is equivalent to the case that the spherical waves is coming from infinity, and when the object will move away from the another stellar object, we can assume that the spherical wave is diverging away towards infinity. So this was a just factor, but this is not important. So the important cases were the what I have discussed the case, that is the phase constants are constant, and one of the wave shown in the red will indicate that the wave is that the spherical wave is propagating outward, and this wave indicates the wave in green indicates that the spherical wave is coming inward, that is moving inward. So this is the actually the linear combination of the two waves, two spherical waves, one moving outward and one moving inward. Now we are going to discuss the case E less than 0. That is the energy. That is, we are going to discuss E less than 0 means that A is also less than 0, because both are directly connected through a constant, through a positive constant. So, and when E is less than 0, it means that we are talking about the case of a bound state. That is, for example, the electron is bound to the nucleus, and such a state, for such a state, the energy of the electron will be negative. That is, the electron has a binding energy, which is a negative energy. The following solution can then be obtained from the equation. That is, from this equation. Solving equation number 11, with the condition that R is a much larger, second term and the third term with the parentheses within the square bracket are 0, only A will survive. Under that condition, we are going to write the solution under the condition that A is a negative, and the solution will become this. So U of R is equal to C1 e to the power plus k plus kappa r. Here is not k but kappa r, and plus the second solution is c2 times e to the power minus kappa r. And again you see that we have written two solutions, because both are the solutions of the same differential equation, that is e to the power plus kappa r and e to the power minus kappa r. Both satisfy the solution of the equation when the energy is negative. And we have in equation number 16, we have given you the sum of the superposition of these two solutions, that is C1 e to the power plus kappa r plus C2 e to the power minus kappa r. And these C1 and C2 could be different from the C1 and the C2 I have used earlier. So these C1 and C2 could be different. Now as r goes to infinity, e to the power plus kappa r will also go to infinity, which contradicts the known physical condition. To justify this, that is e to the power plus kappa r goes to infinity, and we don't want this to be go to infinity. So what we are going to do is that we are going to choose C1 to be equal to 0. Under that condition, we are left with the option that U of R is equal to C times e to the power minus kappa r. You know that when R will increase, then of course this solution will vanish out, which is of course which is known to our physical conditions, that when the electron is further away from the nucleus, then of course the wave function related with that electron will also decrease, and ultimately it becomes equal to 0 for large values of R. So now this capital R is equal to C over R and e to the power minus kappa r. So again, you see that each time we are writing two solutions, one solution in terms of U of R, and the other R solution, which is the actual solution, is capital R as a function of R is equal to C over R times e to the power minus kappa R. So equation number 18 gives our real solution. If you take the mod value of this capital R, that is the mod of capital R, or more accurately, the absolute square of capital R, this will give you the probability of finding the electron in a given space. So you see that if you want to find out the electron in a given space, you can evaluate the quantity which is absolute square of capital R. But you know that this is a constant C over there in equation number 18, which may you call as a normalization constant. This constant first of all will be determined, and after plugging this constant over here, you can use this capital R over here. That is, you can evaluate the term absolute square of capital R, which will give you the probability of finding the electron in a given space, that is as a function of R. The probability decreases exponentially with the increase in R. Since the wave function also decreases with increase in r, the probability will also behave similarly. That is, the particle is localized within a certain area in space. This is the quantum mechanical analogy to the closed elliptical orbits of the classical physics. Note that there are no electronic orbits in quantum mechanics. So the concept of classical orbits is completely forbidden in quantum mechanics. So in quantum mechanics, we talk about in terms of the probability of finding the electron, or in terms of the probability density, or in terms of the charge density. We don't talk about the classical orbits in quantum mechanics. The radial wave function of hydrogen atom. You see that before that I have discussed the two cases, and there you see that I have ignored these terms. Let me show you. For example, using the assumption that r goes to infinity, I have discarded the term L into L plus 1 divided by r square. This term was discarded, and the another term, which is V prime of r, that is the potential, was also discarded and were set to 0 under the condition that r is very large. Now you see that we, in order to solve the hydrogen atom, we need to keep these two parameters. And this is shown in the differential equation over here, that when we are going to solve the radial part of, or radial wave function of the hydrogen atom, you see that I have written the full wave, the full differential form of the wave for the hydrogen atom as shown in equation number 19. This equation has been transformed in equation number 10.5 and is reproduced below. So you see that we have this equation was transformed as given in equation number 10.5. Similarly, using similar transformation, equation number 19 can be written as given as shown in equation number 20 after transformation. Similar to the transformation that was done for the case of 10.5. So we have now d square of capital R divided by d r square plus 2 over r, and then the derivative of capital R with respect to r, and within the square bracket we have a minus v prime of r minus L into L plus 1 divided by r square, and outside this bracket we have capital R, and this the sum of all these three terms is equal to 0 as shown in equation number 20. Here V of R is the central potential, or V prime of R is also the central potential. That is the Coulomb potential for a hydrogen-like atom. So V of R is given is defined as for a hydrogen atom to be equal to V of R is equal to minus Z E square over 4 pi epsilon naught R. We have been using this potential in previous slides also. So this is the Coulomb potential for the case of the hydrogen-like atom, because Z is present. If you want to adopt this potential for the case of hydrogen atom particularly, you can choose Z is equal to 1, which is the atomic number. Let us introduce a dimensionless variable rho. You see that we want to now to solve this equation in a dimensionless parameter, and the dimensionless parameter is going to be, we are going to introduce is the rho parameter. Rho is equal to 2 times kappa times r, because kappa has a dimension of 1 over length and r has the dimension of length, so rho has a rho is a dimensionless quantity. So this is labeled as equation number 22, and the parameter a, which we have defined earlier, capital A is equal to 2m naught over h bar square times capital E, and that is equal to minus kappa square. So we are now going to label this equation as a 10.23. So you see that to introduce rho in equation number 20, the equation can be divided by 4 kappa square. So in order to introduce equation number 22 into equation number 20, we are going to divide equation number 20 by the parameter 4 kappa square. And the transformation is shown in equation number 24. So you can see that we have created the term 2 kappa r everywhere where r were present. So wherever the r was present, we have completed the term, that is 2 kappa r was introduced there. So the term, for example, a over 4 kappa square, since r is not present over here, so we have left this as such. And similarly, v prime of r was divided is divided with 4 kappa square. The rest of the term where r was present, we have introduced the whole, we have constructed the whole term, that is 2 kappa r. And you know that the wave function capital R, which is a function of R, can also be written as the capital R as a function of rho over 2 kappa. Because you can take the value of R from equation number 22. If you take the value of R from equation number 22, it becomes rho over 2 kappa. So I have introduced the value of R in this equation number 25 by rho over 2 kappa. And this R with a variable of 2 over rho over 2 kappa is simply written as R prime, because we are introducing over here not R but R prime as a function of rho. And R prime of rho is equal to capital R as a function of rho over 2 kappa. Okay, now combining equation number 7 and equation number 21. You see that in equation number 7 we defined this function v prime of r, which was equal to 2m0 over h bar square into v of r. And here I am going to introduce the value of v of r from equation number 21, which is shown in the parentheses, which is equal to minus z square over 4 pi epsilon naught r. So you can write this one in a more appropriate form, which is minus 2 over r, and then the rest of the terms have been written in parentheses. So now I can write this term in parentheses by a value which is capital B, because all the parameters within the parentheses are constant. M naught is the mass of the electron is constant, and the atomic number of an atom is also constant. Charge of the electron is also constant. H bar, which is the reduced Planck constant, is also constant. Epsilon naught is also constant. So all these terms within the parentheses are constant, and I am going to represent this parenthesis by the value capital V. So now I have V of R, that is the potential V prime of R defined to be equal to minus 2B minus 2B over R, as shown in equation number 22, where B, capital B is equal to M naught Z E square over 4 pi epsilon naught H bar square. This is equation number 27. Now using equation number 22, equation number 23, equation number 25, and equation number 26 into equation number 24, we get the following equation. So let me show you equation number 23, 24, 22. This is equation number 22. Also 22. Also you can see equation number 23 given. Also you can notice equation number 25, equation number 26, equation number 27, and I am introducing all these equations into equation number 24, and finally you will get this equation given in as equation number 28. So you see that this is the equation which we have transformed in a dimensionless variable rho. Because we wanted to solve this differential equation, and we wanted to transform that one in its simplest form. The wave function should decay exponentially at large distances. This is what we require, that the wave function should decay exponentially at large distances. It will be seen later that a trial solution of the exponentially decaying form will be appropriate. So we are choosing R prime to be equal to e to the power minus rho by 2 multiplied by a function which is v of rho. So we are choosing this as the solution of equation number 28. That is, we have this equation as a 28, and we are choosing and we are suggesting equation number 29 as the solution of equation number 28. And under the condition that we are assuming that the solution should decay exponentially at large distances. So that's why, and v which is a function of rho, is still unknown. So we have to, if we can find out v as a function of rho and plug in the value of v of rho over here, then of course the function r prime, which is the solution of equation number 28, will be known to us. So in order to find that one, first of all, we carry out the derivative, that is dr prime over d rho, and also the double derivative of r prime with respect to rho. We are going to evaluate these derivatives so that we can plug in these derivatives there. And these derivatives will be calculated using equation number 29. So this is the first derivative that I have calculated. And this is the second derivative that I have calculated. These derivatives are very simple to calculate. So you see that I have shown one derivative d over d rho in the blue. The other derivative d over d rho is shown in green. So that when the blue derivative operator will operate, I shall get the blue terms over here, and when d over d rho, which is shown in green, will act on the term within the parentheses, it will produce the terms which are shown in green. So now I have the blue terms and the green terms, and now I am writing the blue terms separately and the green terms separately, and the terms which are common to the blue and green term, which I can add them, are shown in red. And both terms are equal to minus half e to the power minus rho by 2 and dv over d rho. So you can add these two terms. Now I am going to evaluate this 2 over rho times dr prime over d rho. And dr prime over d rho has been calculated over here. For example, you can see over here. And I need to multiply it by 2 over rho on both sides. So I can evaluate this term shown in equation number 31. So 2 over r times d r prime over d rho is shown on the right hand side in equation number 10.31. And you see that here again I have shown one terms in red, because these terms and the other two red terms shown in equation number 30 can be combined together. Whereas there will be three other terms, that is the term in the blue in equation number 30, the term in the green in equation number 30, and the term in the black in equation number 31. The other three terms which are shown in the red can be combined, and the result is given over here. So you can add the two derivatives and you can combine them in the following form as shown in the final step of equation number 32. Now I can use equation number 32 into equation number 28, and the resulting wave equation takes the following form. Now you see that this is the wave equation in the variable v double prime. And you know that v prime, where v is actually present over here. So v is unknown over here. So we need to find out v over here. So if v as a function of rho is known, we can plug in the value of v as a function of rho over here in equation number 29, and the solution r prime will be known. And once r prime is known, we can find out r and r as a function of rho over 2 kappa, and we can also find then capital R as a function of r. So you see that now our final differential equation in the parameter v is shown in equation number 33, which is v double prime plus, within the parentheses we have 2 over rho minus 1 times v single prime. V single prime in that the v double prime in its double derivative of v with respect to rho, that is dv square, that is d square v over d rho square. And this v single prime is actually the first derivative of v with respect to rho. And then we have the term in the square bracket, which is b over kappa minus 1. And this is shown in parentheses multiplied by 1 over rho. And then we have minus L into L plus 1 divided by rho square. And outside this square bracket, we have rho. And then we have all these terms summed to equal to 0. So this is the differential equation shown in equation number 33 that we would like to solve. So once this is solved, it means that we could be able to find out v as a function of rho. So in order to solve this equation, we are suggesting a solution in the form shown in equation number 34. This differential equation is satisfied by a trial solution in the form of a power series written in row. So we are suggesting a solution of V as a function of rho to be equal to a sum of series solution, which is equal to rho to the power mu, and the summation is over V is equal to 0 to infinity, and we have a V times rho to the power V, and we can combine, we can send rho mu inside the arguments of the sigma function. Then we have this summation sigma, which is going from V is equal to 0 to infinity, and this sigma contains the argument which is AV times rho to the power V plus mu, and the first element of this series is at least not equal to 0. So this A naught is not equal to 0. This is our assumption, because at least one of the term in the series should not be equal to 0, and we are choosing the first term to be not equal to 0. So you see that this V of V in terms of the series function shown on the right hand side of equation number 34 will be used as a trial solution for equation number 33. So it means that from this one, what we need to do is that we need to calculate the single derivative V prime and the double derivative using equation number 34, which will be V double prime shown in green. Exponent mu and the coefficient AV are to be determined. So you see that this solution will be known only if mu is known and AVs are known. So these coefficients, which are the coefficient of the series, which is AV and mu, if these are known, then of course the solution V as a function of rho is known. So we have to find out these two variables of the problem. That is the exponent mu and the coefficients AV are to be determined. First and the second derivatives are found as given. So using the equation number 34 shown over here, we need to calculate the first and second derivatives, which are listed in equation number 35 and 36. So using V single prime, V double prime from equation number 34, 35 and 36, and using them in equation number 33 and setting the coefficients of the lowest power of rho to the power mu minus 2 equal to 0, we get. So you see that here what we are going to do is that we are plugging in the value of rho over here in row of value of V in equation number 33, value of V prime in equation number 33, value of V double prime. So we are using V single prime, V double prime from this equation, V single prime from the next equation, that is from equation number 35, and V double prime from equation number 36, using these value in equation number 33 over here. And since this equation 33, the resulting equation will contain series function. So what we are going to do is that in order to solve that one, we are setting the coefficient of the lowest power, which is rho to the power mu minus 2 equal to 0. So you see that this is the way of solving the differential equations using the power series. If you are trying a trial solution in the form of a power series, you can choose some constants to be equal to 0. So here we are choosing the coefficients of rho to the power mu minus 2 to be equal to 0. So you see that rho to the power mu minus 2 is present in all the three terms of the differential equation. So to obtain the coefficient of rho to the power mu minus 2 from V double prime, we set V is equal to 0 in equation number 10.36. So if you choose 10 in equation number 36, if you set V is equal to 0, then you see that the coefficient that we are left with is rho to the power mu minus 2. And its coefficient will be this, And you know that in order to find this coefficient, we have set the value of v is equal to 0. You know that if you set the value of v is equal to 0, you need to set the value of v over here, and you need to set the value of v is equal to 0 over here. And when you fix the value of v, then of course this sigma notation will be eliminated because a particular value of v is selected. Now, to obtain the coefficient e to the rho to the power mu minus 2 from this term, that is from the second term, we set v is equal to 0 in equation number 35. And we get the desired coefficient will be 2 mu naught mu. So similarly, you see that if you multiply this rho with the term 2 over rho, because you know that v prime appears in this equation. V prime appears in this equation with the parameter 1 and also with 2 over rho. So if 2 over rho is present, then of course rho will also appear over here. But the coefficient is e to the power minus rho by 2. And then you see that you have also the value of v prime. So put the value of v prime over there from equation number 35. So once v prime is inserted there, you can similarly set the coefficient. You can similarly calculate this coefficient e rho to the power mu minus 2 by setting the value of v is equal to 0. And then you need to set the value of v is equal to 0 everywhere where v is present, and the summation, that is the sigma summation, will also be eliminated because we choose the value v is equal to 0. And then of course we can also write the coefficient of rho to the power mu minus 2, and the coefficient of rho to the power mu minus 2 will be equal to 2a naught mu. So from the v double prime term, the coefficient was a naught times mu minus 1. And from the next term, which was the v prime term, the coefficient was equal to the coefficient of rho to the power mu minus 2 will be equal to 2 times a naught times mu. And from the third term, if you want to find out the coefficient of rho to the power mu minus 2, you again set the value of v is equal to 0 in the third part, and then of course the coefficient will be minus a naught times L plus 1. So you have three coefficients, and the sum of these three coefficients will be equal to 0. The coefficient is what I have shown in the red, the second coefficient I have shown in the green, the third coefficient I have shown in black. So I have summed up these coefficients, and of course this is equal to 0. So you see that from these equations, from these coefficients, what we get? We can combine the desired terms in the following form, and then since we can also write, since in this equation a naught is not equal to 0, it means the rest of the terms are equal to 0. So if you set the rest of the term equal to 0, then of course you can find this result, that is mu into mu plus 1 is equal to L into L plus 1. There are two solutions. One obvious solution is mu is equal to L. So if you choose mu is equal to L, then of course the equation is satisfied. This is a very obvious solution. The second solution is you set mu is equal to minus L minus 1. If you try this solution, in this equation, the equation is also satisfied. So these are the two obvious solutions. For mu is equal to minus L minus 1, the function rho as a function, v as a function of rho diverges at the origin. Because if you try this solution, then in the final solution, you have 1 over rho raised to the power L. And then of course this solution will vanish out or will diverge out at the origin, because you have 1 over rho, and 1 over rho means the rho is in the denominator. So at the origin, that is at rho is equal to 0, the term will diverge out. So this solution will be discarded, because this solution causes the trial solution, this one, to diverge, and we don't want this solution to diverge out. So it is required that the solution obtained from the Schrodinger equation should be well behaved in the entire region. So the solution mu is equal to minus L minus 1 will be discarded. Only the solution that is mu is equal to L will be chosen. Because with this solution, the wave function, which is the capital R, which is a capital R star, that is capital R star, will not diverge. Let us set the coefficients of the higher powers of rho. V not equal to 0, equal to 0. Now you see that we are choosing higher values of coefficients. Before that, when we choose this one, we choosing v is equal to 0. You see that v is equal to 0, v is equal to 0, v is equal to 0. Now we are setting the condition. We are choosing higher coefficients, and we are assuming that now v is not equal to 0. And we are choosing this coefficient rho to the power v plus L minus 2. So we are computing the coefficient of this term. And now we want to set, we shall sum up all the three coefficients from the three terms, and we sum them, and then we shall set them equal to 0. And you see that I am not computing these coefficients because I have calculated the previous coefficients. You can calculate those coefficients in a similar manner. So these are the coefficients of rho to the power v plus L minus 2. And I have summed up these three coefficients from the first three terms, and then I have summed them equal to 0. So you have these coefficients which are summed to equal to 0. Where n is shown to be equal to n is equal to capital P over kappa. The n marked in red in equation number 37 has been shown as n is equal to capital B over kappa as shown in equation number 38. Now you see that we have to analyze the terms in equation number 37. So the following recursion formula can be obtained from equation number 37. We have AV on the left hand side, and on the right hand side we have some terms, and also we have a to the a with subscript v minus 1. So we have a relationship of av with a v minus 1. So in equation number 39, if one of the coefficients of a is known, then all the rest of the coefficients of the series can be computed using the recursion formula shown in equation number 39. So at least we want to know at least one of the parameter of the series elements, that is the a term. So at least one of the a terms needs to be evaluated. And you see that this series in the function that we have defined as a solution, for example, this is the solution that we have defined. Here v parameter starts from 0 and goes up to infinity. So this is an infinite series solution. So we want to see that if we can we trunk this solution so that we can have a definite and well-behaved solution. For that one, let's analyze this recursive solution, this recursive formula. There are two possibilities. The number one possibility is that the chain of A's is terminated somewhere. That is, we have a finite series of terms. The second option is that the chain of A's is not terminated. That is the second, that is the term, that is the series A, that is the series with coefficients A is infinite in series. So let's talk about the second option further. In this case, there will be an infinitely many terms. Mathematically, rho of v is practically equal to an exponential function which diverges at infinity. So since there will be many terms involved, so you see that we have to choose large values of v, and of course v of rho will be diverging. So it means that we should discard the choice that the terms that the A's is not terminated. So it means that the second option will be discarded and we shall work on the first option, that the chain of A's should be terminated. So that we shall have V of rho to be a function which is an exponentially decaying function. So choosing the option A, the chains of A's will terminate only if n is an integer. So you see that here the problem is that in order to terminate this series given by this recursive formula, n must, the condition mathematically, the mathematical condition on this recursive formula is that n must be an integer. So if n is an integer and a cutoff, then a cutoff is obtained for v is equal to v naught. And that v is equal to v naught will be obtained as v naught is equal to n minus L. So you see that n, you know that L is already an integer. We have proved it earlier in the slide number 9a and the slide number 9b. We have already established that the orbital quantum number L is an integer. But here you see that here we are putting a condition on the principal quantum number n. Here n is a number, but you know that we shall call later it as the principal quantum number. So here we are putting a condition that n is also an integer. And the cutoff is obtained for the value of v is equal to v naught. V naught is going to set the cutoff value for the solution. For the infinite series solution, the solution will be terminated, will be limited in size by choosing v naught as the cutoff value. And this v naught is equal to n minus L. L we know that is an integer. So here we are imposing the condition that n is also an integer. So V naught, since V naught is not the first term, but it is the term but it is a term which is exists at the large, which exists. So here V naught is much greater than 1 because V naught is not the first term of the series. Because the series we are using number of terms should be present in the series because we are truncating the series at a cutoff frequency V naught. So of course V naught is at least must be greater than 1. So it means that n minus L is greater than equal to 1. Okay, this implies that n minus L is greater than equal to 1, or n minus 1 is greater than equal to L, or equivalently you can write that L is less than equal to n minus 1. So you see that before that we were using L, and there was no limit on the value of L. Now the limit comes over here, that L, the orbital quantum number, should be less than by 1 from the principal quantum number. So the maximum value of L should be equal to n minus 1. This is what we have written as equation number 40. So L should be less than equal to n minus 1, where n is an integer. So n is the principal quantum number and L is the orbital quantum number. So equation number 38 is read with n is equal to 1, 2, 3 and so on being integers. So let me show you equation number 38. So this is equation number 38. And in this equation, we have established that n should be an integer. So squaring both sides of equation number 38 and plugging in the values of capital B and kappa from equation number 27 and from equation number 23, we respectively get the following relation. N square is equal to B square over kappa square. The value of B is m naught z e square over 4 pi epsilon naught h bar square, and the value of kappa is kappa square is, the value of kappa square is minus 2m naught over h bar square times E. So simplifying, so solving this equation for the value of capital E, we get this relationship shown in equation number 11, shown in equation number 41, that capital E is equal to minus half times m naught over 4 pi epsilon naught square, and then z square over E to the power 4 over h bar square, and then 1 over n square. You can recognize this formula. We have also discussed this formula in some of the previous slides. For example, in slide number 3. So which is the binding energy formula for an electron in a hydrogen-like atom and agrees with the Bohr's atomic theory and is the same as derived in equation number 3.14. So the first time derivation, you can consult equation number 3.14, that is slide number 3 and equation number 14. And so you see that we have using this formula, we have established the energy formula that the energy of that is the binding energy of the electron is given by the relationship shown in equation number 41. And this is in agreement with the Bohr's atomic theory. This is the binding energy of the electron in a hydrogen-like atom. The discrete values of n, because n takes integer values 1, 2, 3, and so on. So the discrete values of n and hence that of E. So if n takes discrete values, then n will also take, then energy E will also take discrete values. So, and hence that of E are associated with the truncated series of the A coefficients. And you know that the discrete values of the concept of discrete values, or the concept of the discrete values of n, and thus the discrete values of E comes from the concept that the series of A's was truncated. This restricts the wave function should vanish at infinity. So once the series is truncated, it means that the series does not contain infinite coefficients, and of course that the wave function should also vanish at infinity, because the wave function now has a truncated form. So you see that here E is the binding energy, which is negative. The case of E to be greater than equal to 0 when the electron is not bound to the nucleus, that is the electron behaving as a free electron, for which the energy is greater than 0, that is the unbound state. So E greater than 0 represents unbound state. The energies form a continuous distribution of values, because when the electron is free, it can have any energy. It can take any continuous value of energy. So this case will not be discussed here. The series of A's has a cutoff frequency at V is equal to V naught, and this V naught was equal to n minus L. And V of rho becomes a polynomial, because since we have a solution in the form of a series function, and once the series is truncated, it will behave as a polynomial. The trial solution then takes the following form. So R prime is equal to e to the power minus rho by 2 times V of rho, and this V of rho, now we have determined some features of this V of rho, which is not an infinite expansion, but V of rho is equal to sigma with V from equal to 0 to V naught value, and V naught is equal to n minus L, and then we have the same argument, that is AV times rho to the power V plus mu. But the only good thing is that now we have a truncated series, and it is truncated by the value V naught, because the upper bound of this is V naught, which is equal to n minus L. Where the parameters are defined as. So in this solution, the AVs are defined by this solution. And you know that this is the same recursive relationship that we have obtained. We have written it from equation number 10.39. And of course, the first element of this series is not equal to 0. So A is not equal to 0. The second, the thing we have found about this solution is mu is equal to L. So we have found a particular value of me also, and the rho is equal to 2 kappa r. This is what we have obtained from equation number 22. So all the parameters of this series shown in equation number 10.42 is known. So it means that the solution, that is V of rho, is known. So it means that R prime is known. Now you see that we can express this solution, that is the solution given in equation number 10.42, can be expressed with more well-behaved function, which is shown in equation number 43. So the solution is R and L, that is the solution capital R depending upon the variables N and L, which are the quantum numbers, principal quantum number and the orbital quantum number, and capital R is a function of a small r, which is the distance from the nucleus. This is equal to NL, N capital N with the subscript of small nl, where small n is the principal quantum number, small l is the orbital quantum number, capital L is the normalization constant, and then we have the term which is equal to e to the power minus kappa nr, because we have substituted the value of rho there, and then r to the power l, and then we have this function which is capital, which is represented by capital L, and it is called the associated Laguerre polynomial. So this capital L is actually the associated Laguerre polynomial. It has a superscript as 2l plus 1, and it has a subscript as n minus l minus 1. And the argument of this associated Laguerre polynomial is 2knr. You can also write k as simply k, or you can also attach a subscript with the subscript n with k. Both r will be equal. So with the subscript, when you attach a subscript n with the k, n with the kappa, it means that the kappa now depends upon the value of the principal quantum number n. But if you don't want to represent kappa n with the kappa, that will also be equally okay. Now this is the Laguerre polynomial, capital L. So the capital L, that is the Laguerre, that is the associated Laguerre polynomial, is defined, has been defined in equation number 44. That is L and K as a function of x is equal to summation from m is equal to 0, m is equal to 0 to upper value n, and minus m raised to power m, then n plus k and n minus k. These are the variables that you use in the binomial series expansion, that is the NCR variable, and then multiplied by x to the power m divided by m factorial. So this is the definition of the associated Laguerre polynomial. So you can similarly expand the Laguerre polynomial given in equation number 43 in the form of this series. And when you expand the Laguerre polynomial in equation number 43 by using the expansion function shown in equation number 44, you will get the same term as shown in equation number 42. Since these are the laborious calculations, I am not going to do these calculations. So I have the solution of the radial wave function of the hydrogen atom given by in equation number 43. But there is one thing that is to be determined is the normalization constant of the problem, which is capital N with a subscript of NL, small n, small l. So if we determine this normalization constant, then of course the whole wave function is determined, because all the rest of the parameters are known. So capital L with the subscript n minus l minus 1 and the superscript 2l plus 1 is actually a mathematical symbol for the polynomial, which we call as the Laguerre, associated Laguerre polynomial. So this can be obtained from the so-called Laguerre polynomial with L and the subscript of n minus l minus 1. So if you omit the superscript, then of course it is simply called as a Laguerre polynomial. But if you specify the superscript, it will be referred to as the associated Laguerre polynomial. So this is the relationship. And this can be obtained from the so-called Laguerre polynomial L n minus l minus 1 differentiated to l plus 1 times, as shown in equation number 45. So this is the relationship that you are going to differentiate l n minus 1 on the right hand side with d over d rho 2l plus 1 times differentiating the L function L of n minus L minus 1 as a function of rho. If you differentiate this 2l plus 1 times, you will get the associated Laguerre polynomial represented as capital L with a superscript of 2l plus 1 and the subscript of n minus L minus 1. The superscript 2l plus 1 indicates the order of differential that we have used on the right hand side. Now now we want to define capital L as a superscript as a subscript of n minus L minus 1 as a function of rho. That is, we are going to define the Laguerre polynomial in equation number 46. So Laguerre polynomial in equation number 46 has this definition: e to the power rho divided by the factorial of n minus L minus 1 times the differential with n plus with an order of n plus L minus 1, and the differential is with respect to rho, and the differentiated term is shown in parentheses, which is e to the power minus rho, and then rho to the power n minus L minus 1. So you see that I have defined the associated Laguerre polynomial in equation number 45 in terms of the simple or standard Laguerre polynomial on the right hand side of equation number 5, and equation number 46 I am going to define the standard Laguerre polynomial written on the left hand side, and the terms in terms of the terms written on the right hand side in equation number 46. Now I am going to give you some definitions of some parameters which you can use. For example, definition of standard Laguerre polynomials is this: Ln as a function of x is equal to e to the power x over n factorial times the nth order derivative of with respect to d over dx of the term which is e to the power minus x and x to the power n. So this is the definition of the standard Laguerre polynomial. Now the definition of the associated Laguerre polynomial is given over here. And the relationship between the associated Laguerre and the standard Laguerre polynomial are given over here. For example, this is one of the solution, and this is another relationship. These are the two relationships where you can convert these relationships. That is, the standard Laguerre polynomial can be converted into associated Laguerre polynomial. So you see that these are the definitions of the standard Laguerre polynomial, the associated Laguerre polynomial, and the relationship of the associated Laguerre polynomial in terms of the standard Laguerre polynomial. Now you see that the next problem is to find out the normalization constant capital N with a subscript of NL. To find this one is found through the condition called normalization condition, which is given over here in equation number 47. So you are actually taking the absolute square of the radial wave function, and if the wave function is a positive quantity, you can simply take the square of that quantity and integrate that one over the allowed range of variable r, that's from 0 to infinity, because the r can take a minimum value of 0 and can take the maximum value equal to infinity. So you are taking the integral of absolute value of r square as a function of r, multiplying it with r square, and then taking the integral with respect to dr and setting this parameter equal to 0, because this gives you the probability of finding the electron in the region from 0 to infinity will be equal to 1. And this is also known as the normalization condition. So you see that kappa has the dimension of 1 over length, and from equation number 34, you see that the value of the kappa is given. That is kappa was equal to b over n, and we have the value of a b, which I am going to plug in, and finally the value of a kappa that you get is m0 over 4 pi epsilon naught times z e square over h bar square times 1 over n, as shown in equation number 48. So this is the value of kappa. So after evaluating, that is substituting the value of the radial wave function, the absolute value of the value of capital R from the previous equation, that is from this equation number 43, which gives you the solution of the radial wave function in terms of the associated Laguerre polynomial. And you know that now the value of kappa is also known to us. So substituting these values and integrating using the normalization condition shown in equation number 47, and using also the value of kappa in the previous solution, then you see that you will get this value of normalization constant. So after evaluating the normalization constant capital N, equation number 10.47, and using equation number 10.47 and plugging its value in equation number 10.43, the complete radial wave function of the hydrogen like atom can be written as, that is equation number 43, that is radial part of the wave function shown in equation number 43, after using the normalization constant and after finding the normalization constant n and plugging back the value of normalization constant n, the solution shown in equation number 43 will take the following form as shown in equation number 49. So you can see that the radial part of the wave function as a function of rho depends upon the square root of the value, which is 2z over n times a naught raised to power 3, and then multiplied by the factorial of n minus l minus 1 divided by 2n times the factorial of n plus l. So these terms are contained in the square root, and outside that square root we have e to the power minus rho by 2, and then the rho to the power l, and then the associated Laguerre polynomial with the subscript n minus l minus 1 and a superscript with 2l plus 1, and Laguerre polynomial as a function of rho. And the value of rho over here is 2 kappa r. So if you substitute the value of 2 kappa r, you can obtain this solution in terms of the radial quantity capital R. In terms of the radial quantity small r. Here in equation number 49, the solution of the radial part of the hydrogen like atom is in the form of a normalized variable rho. And you know that here in the square root you can see the parameter a naught. A naught is actually the Bohr's orbit. The first radius, the radius of the first radius of the electron in a hydrogen atom is referred to as the Bohr's radius in its ground state, which is represented by a naught. So don't confuse a naught with the first term of the series. Here a naught is actually the Bohr's orbit, Bohr's radius. Now you see that you can compute the value of rho. So rho is equal to 2 times kappa r. You can put the value of kappa over here, and then simplifying over here, you can have this relationship. And I have shown some terms in the red, and the terms in the red are actually 1 over a naught, where a naught is the Bohr's orbit. So over here you see that in equation number 51, I have shown rho is equal to 2 times z times r over n times a naught, where a naught is the Bohr's radius and is equal to the reciprocal of the term shown in the red over here. So n is equal to 1, 2, 3, and so on is actually the principal quantum number. L is equal to 0, 1, 2, 3 on up to n minus 1. So now you see that L is restricted by the value n minus 1. Is the azimuthal quantum number, also known as the orbital angular momentum quantum number, or simply as the orbital quantum number. Normalization constant n with the subscript NL, or the square root term in equation number 49, ensures that the total probability of finding the electron anywhere in space around the nucleus with the rho going from rho is equal to 0 to rho is equal to infinity is 1, or r small r going from 0 to small r up to infinity will be equal to 1. Now you see that over solution of the solution of the hydrogen atom for the radial wave function, which is shown in equation number 49, contains some terms which are important. That is e to the power minus rho by 2. This is an important term. The second term is rho to the power L. This is equally important. And the third term is the associated Laguerre polynomial, which is also very important. So let's explain what are the meaning of these three important functions or terms. The exponential decay term, which is e to the power minus rho by 2, ensures that the wave function would approach to 0 as rho increases. So you see that you can express this term as 1 over e to the power rho by 2. So when rho increases, this term becomes much greater, and this will make the wave function to go to 0. The power law term, which is rho to the power L, and you know that L is a positive quantity starting at least from 0 and taking integer values L is equal to 0, 1, 2, 3 and so on up to n minus 1. So rho to the power L ensures the wave function must vanish at the site of the nucleus by creating centrifugal barrier where rho is equal to 0, the rho goes to 0 for L greater than 0. And you know that L is greater than 0 for p, d and f orbitals. L is equal to 0 for s orbital. And if you take L greater than 0, this will be, for example, for L is equal to 1 for the p orbital, L is equal to 2 for d orbital, L is equal to 3 for f orbitals. So for greater values of L, this e to the power rho to the power L ensures that the wave function must vanish at the site of the nucleus. So for all the p, d and f orbitals, this term will ensure that the wave function should disappear or should vanish at the site of the nucleus. That is at the point where the nucleus exists. That is where r is equal to 0. Because you can relate rho in terms of 2 kappa r, and there you can establish that this quantity will not allow the wave functions related with the spdf orbitals of the hydrogen atom to be equal to be to have some values at the site of the nucleus. These must have, that is the wave functions corresponding to these pdf orbitals must vanish at the site of the nucleus. Now the Laguerre polynomial is a polynomial of degree n minus l minus 1. The subscript of this one gives you the degree of the polynomial, and the polynomial will cross the 0 axis exactly equal to n minus l minus 1 times excluding the origin and the infinity. So you see that the subscript n minus l minus 1 will give you the number of zeros that the polynomial will cross the axis, will cross the 0 axis except the region, except excluding the region of the origin and the infinity. Now you see that I am going to give you the plots of the radial wave functions of the hydrogen atom. So this is the first plot. That is the plot of the radial wave function of the hydrogen atom for 1s electron. You know that for the 1s electron, the principal quantum number is 1, and S mean that the orbital quantum number is equal to 0. And the radial function, which is plotted along the vertical sides by putting the value of n is equal to 1 and L is equal to 0, you will see that the wave function is approaching the nucleus because the nucleus is existing at r is equal to 0 value. So the electron can come very close to the nucleus over here when it is in the first that is when the electron in the first orbit, the electron can approach to the nucleus. And you know that when the electron goes away from the nucleus, the wave function of the electron goes to decay very fastly and becomes zero. When the electron is away at a distance equal to 8 times the a naught, where a naught is the Bohr's orbit, is the Bohr's radius. So when the value of electron, when the radial value of the electron is at least 6 to is at least beyond the value of 6 times the 6 times the Bohr orbit, then of course the wave function will vanish, will start vanishing and will completely vanish at a value when it is equal to 8 times the Bohr radius. So you can notice that the trend of the wave function, the radial wave function corresponding to 1s electron in the hydrogen atom. So now we are going to other wave functions. One corresponds to 2s electron. 2s electron means that the principal quantum number is 2, and s means that the orbital quantum number is 0. And 3s, principal quantum number is 3, and s means that the orbital quantum number is 0. So you see that I have shown the two colors in blue and in brown, light brown. Then you can see that I have plotted these two functions simultaneously on the same plot. And you can see that how many times these plots cross the zero function. And that should be equal to n minus L minus 1. So it means that the both functions will cross the zero axis at least one times only. So the blue line crosses the function one times, and the blue and the gray and the brown function also cuts the wave function twice, because that is n minus L minus 1, that is 2. So it will cross the function, that is the curve with the light brown will cross the function with the velocity zero axis twice, whereas the blue function will cross the zero axis only once. So you see that these are the plots of the radial wave functions of the hydrogen atom for the 2s and for the 3s electrons. And you know that when you move away from the nucleus is residing at the r is equal to 0 value. So you see that this electron can also come closer to the nucleus. So it means that the electron with the 2s can even closer to the nucleus, because the value of the wave function is higher there in comparison with the 3s electron, which can come closer to the nucleus, but further away from the further away as compared with the 2s electrons. And you see that their progression towards the with greater value of the wave function, with greater radius distance from the nucleus has been shown. So you see that when it crosses the zero axis, it means that the electron cannot exist at these particular values, whereas it can exist at other values. You see that the wave function can also be a negative quantity and a positive quantity, whereas the probability density will always be a positive quantity, because there you calculate the absolute square of the radial wave function. So you see that this is the radial part of the wave function for the 2s and 3s electrons. Now you see that here I am going to plot 3 for the 3 electrons, radial, the plot of radial wave functions of the hydrogen atom for the 2p electron, for the 3p electron, for the 3p electrons. For the 2p electron, we have n is equal to 2 and L is equal to 1. For the 3p electron, we have n is equal to 3 and L is equal to 1. And for the 3d electron, we have n is equal to 3 and L is equal to 2. And you see that the curves in 3 different colors are shown, so that you can discriminate the curve of 2p from the 3p and from the 3d electrons. And you see that when the electron is in the 2p state, 3p state, or the 4d or the 3d state, the electron will stay away from the nucleus. It cannot come closer to the nucleus as in comparison with the 3s, with the 2s, with the 1s and the 2s and the 3s electrons, as we have discussed in the last two previous slides. So you see that the electron will start from zero. That is, the beyond this region, the electron cannot come closer to the nucleus. And you see that after that one, you see that the probabilities of the electrons will increase as you move away from the center of the nucleus. But you know that for the 2p electron, it will smoothly decay to zero. Whereas for the 3p electron, which is shown in the light brown, it will cross the zero axis once and then it will go to zero. And for the 3d electron, it will cross the term. It will not cross the term because n minus 2 minus 1 will be equal to 1 and will be equal to 0. So it is not going to cross the zero axis. So these are the three axes, and you can compare how the wave function behaves for the three cases. It will tell us that how closer an electron in these states can come closer to the nucleus, and the peaks indicate that what are the probabilities of occurrence of these. That is, the electrons, for example, the 2p electrons is like to occur in is most readily find at its peak value. Similarly, the 3p electron can be found readily at its peak value, whereas the 3d electron can also be found readily at its peak values. So these are the plots of the wave functions. So in the next, I am going to plot the radial probability density of the hydrogen atom. You know that the radial probability will give you us the opportunity to find out where the electron exists, what are the chances of the existence of the electron as it moves away from the nucleus. And this is given by the quantity that the square of r prime of rho multiplied by d rho. Or more accurately, if the wave function is going in the negative direction, you can also write it as the absolute square of the rho prime multiplied by d rho will give you the probability of finding the electron in a hydrogen atom in a particular direction in space in the interval from rho to rho plus d rho. So in this interval, you can, if you want to find out the probability that whether the electron exists in this region, you can evaluate this quantity. But if you multiply this quantity with the 4 pi rho square, then this quantity will give you the probability of finding the electron in a hydrogen atom at a distance rho in the interval rho and rho plus d rho independent of direction. Again, this will give you the location that you want to find, and you want to determine the probability in the region from rho to rho plus d rho. But you see that here the direction is not important. In any direction, or in 4 pi direction, or in a spherical direction, this will give you the probability. Four pi rho square d rho is the volume of the spherical shell of the electron to be located. The plots of So you see that when we talk about rho and rho plus d rho, it means that we are talking about two spherical shell. Spherical volume shell of the electrons where we want to determine its probability. So 4 pi rho square d rho is the volume of the spherical shell for the electrons to be located. The plots of rho pi, 4 pi rho square times r square of rho and d rho have peaks which are displaced to the regions of greater distance with the increasing quantum number n. So you see that we shall notice in the plots that as the principal quantum number n increases, then of course the peaks values corresponding to these probabilities will move towards right. That is, move towards away from the nucleus. We can also use the real parameter r instead of the normalized parameter rho while plotting the probability. On the next page, we are going to plot the probability density P of R, that is P as a function of R. And here we are going to plot R square times the absolute square of R and L as a function of R prime as a function of NL of R versus the radial distance normalized with Bohr radius A0, that is R over A0, will be plotted along the horizontal direction, and the P of R will be plotted along the vertical direction. That is, we are going to study the parameters, that is how the probability P of R will change as the distance from, as the normalized distance from the nucleus is changed. So these are the plots of the radial probability density for the hydrogen atom. The first plot is for the 1s electron, for the 2p electron, for the 3d electron. For the 1s electron, we have n is equal to 1, L is equal to 0. For the 2p electron, we have n is equal to 2, L is equal to 1. For the 3d electron, we have n is equal to 3, L is equal to 2. And you see that three different colors have been shown, and the probability density for three different colors has also been shown. So for the 1s electron, the probability density is the highest. You see that just after in the region around the values equal to 2 or 3. So it can at the so it has a maximum value of the probability. You can find this 1s electron very close to the nucleus, has the highest probability equal to slightly greater than 0.5. The 2p electron, you see that since the principal quantum number is increasing, for the 2p electron, the 2p electron has a peak away from the peak compared with the 1s electron. And the peak is smaller, that is, the probability is reduced equal to less than 0.2. And for the 3d electrons, you know that the peak has even shifted away from the nucleus around the value of Bohr orbit equal to 10. And you see that it is more flat, that is the electron can be found in a vast region, that is the 3d electron can be found in a vast region, whereas most probably it will occur at a distance equal to 10 times the Bohr orbit. So next we are going to discuss the probability of the 2s electron and 2p electron. For the 2s electron, you can see shown in blue, and for the 3p electron shown in light brown. You can see for the 2s electron, the main peak has shifted towards the right. If you compare it with the previous case, then you would notice that the peak exists closer to the nucleus. But here you can see that the peak has shifted towards the right, but there is a small peak closer to the nucleus. And for the electron with the 3p, since the value of the principal quantum number 3, you can see a shift of the peak further away from the nucleus in comparison with the 2s, with the peak of the 2s electron. And here you can notice that the probabilities is very small. The highest probability that you can find the 2s electron is 0.2. And for the 3p electron, the highest probability is slightly above 0.07. And you can notice on the horizontal axis that as you go away from the nucleus, the probability of the finding the 2s electron and the 2 electron and the 3p electron will be 0. That is, after that you cannot find out these 2 electrons. That is beyond a radius equal to 30 times the Bohr orbit, you cannot find 2s electron and 3p electrons. It means that the 2p, that is the 2s and the 3p electrons, are restricted in this region. Similarly, I am going to give you the probability density plot for the 3s electron. And here n is equal to 3 and L is equal to 0. For the 3s electron, you can again note that there are two smaller peaks and one bigger peak. And this bigger peak indicates that the probability of the existence of electron in this region is less than 0.1. And the electron at the maximum can go up to a distance equal to 35 times the Bohr radius. And the maximum probability of finding out this electron, that is the 3 electron, exist slightly below the 15 times the Bohr radius. And the other two smaller peaks can also be seen. That is, this electron, 3xs electron, can also come closer to the nucleus, because you see that it has small values around the nucleus. So you see that these are the probability curves that I have explained for some important electrons. Now I want to write the full wave function of the hydrogen atom. So you see that the full wave function of the hydrogen atom represented by psi, and the subscripts indicate the principal quantum number n, orbital quantum number L, magnetic quantum number n can be written as the product of two wave function. One is the radial wave function Rn with a subscript n and L as a function of R, and the spherical harmonics with the subscript L and the superscript M as a function of theta and phi. And the spherical harmonics is what we have discussed in slide number 9. So equation number 52 gives you the complete wave function of the hydrogen atom. Here n is the principal quantum number. It takes values from 1, 2, 3, 4, and so on. The azimuthal or the orbital quantum number is L. It takes value from 0, 1, 2, 3, and so on up to n minus 1. And you know that L is present both. The radial wave function has a dependence on L, and similarly the spherical harmonic function has also dependence upon the value of L. And L goes from 0 plus minus n. L goes from 0, 1, 2, 3, and so on up to n minus 1. And then we have the magnetic quantum number, which takes its value from 0, then goes up to plus minus 1, plus minus 2, plus minus 3, and so on up to plus minus L. So you see that these are the quantum numbers. I have given their values, and I have given the conditions that are imposed on them. Now you see that the spherical harmonics can be written as the product of two functions. That is, as the product of associated Legendre polynomial and as the function of e to the power iota m phi. So again, you see that the magnetic quantum number m has its dependence on the Legendre polynomial function and also on the function which is e to the power iota m phi. The associated Legendre polynomial we have discussed in much greater detail in the slide number 9. Now you see that substituting these values from the previous equations, I am writing down the radial wave function over here. This is the radial function from equation number 49, which we have already discussed. And from equation number 42 of slide number 9, the spherical harmonics were written over here. You see that I have written these the terms in the square root. I have indicated the term in red. I forgot to write these terms when talking about equation number 9.62. You must make a correction that these red terms are also present in equation number 9.62. So here I have written the corrected spherical harmonics, and you see that this is the complete harmonic spherical harmonics. So we can put the values of radial wave function and the spherical harmonic wave function over here to write the complete wave function of the hydrogen atom, which is shown over here in equation number 55. So you can see that the square root contains the normalization constant due to radial wave function and due to spherical harmonics. And then we have again the other terms, e to the power minus rho by 2, e to the power minus rho by 2, then rho to the power L, then the associated Laguerre polynomial, and then the Legendre polynomial, associated Legendre polynomial, and then e to the power iota m5. So equation number 55 gives you the complete solution, complete wave function of the hydrogen atom or the hydrogen like atom, because it has a dependence upon the value of Z. So if you take absolute square of y function, which is the wave function, which is the complete wave function of the hydrogen atom, the absolute square of this quantity gives you the probability of finding the electron in a hydrogen-like atom in a particular direction in space, where n minus L minus 1 gives the number of radial nodes. L will give you the number of angular nodes. N minus 1 will give you the total number of nodes, because if you add these two quantities, that is n minus L minus 1 added to L will give you n minus 1, the total number of nodes in the wave function. Now you see that absolute square of psi will give you the probability, and the plot will be three-dimensional. So you see that this is the three-dimensional probability distribution. This is the three-dimensional plot of the wave function psi of 100, that is principal quantum number n is equal to 1, orbital quantum number is 0, magnetic quantum number is 0. So this is the 1s electron. So this is the shape of the 1s electron which is shown, and this is of a spherical form. So now this is the plot of the 2s electron. For the 2s electron, we have the principal quantum number 2, orbital quantum number 0, magnetic quantum number 0, and this is shown in 3D also. You see that there is also a peak inside over here, a small peak contained over here. From at the center of the nucleus, you have 0 over there, and this small region indicates that the probability is increasing, probability or the wave function is increasing, and of course in this spherical region the probability that the wave function is uniformly symmetric and has a shape of this spherical form, and in the central region of that one. And after that one, the wave function at the outer boundary will decrease and will become 0. So at the outer boundary of this spherical shell, the wave function will decrease. Similarly, this is the plot of the 2pz orbital, that is 2pz electron. For the principal quantum number is 2, the orbital quantum number is 1. So this is the plot of the 2pz orbital, that is you can find a three-dimensional dumbbell shape aligned along the z-axis, and the z-axis is taken along the vertical direction. So this is the wave function. The vertical direction of the z-axis shows the blue dumbbell, and the lower one shows the orange type dumbbell. So you can also plot the linear combination of the two wave functions. So here is the linear combination of the two wave functions. The first wave function has the value of n is equal to 2, l is equal to 1, m is equal to 1. And the second wave function has a value of n is equal to 2, l is equal to 1, m is equal to minus 1. And if you combine these two wave functions linearly and multiplying with the factor iota by square root of 2, so that you can have a real value in the plot, then of course the wave function is shown in figure. That is it is a 2py, that is it a py dumbbell shape, that is it is a py three-dimensional dumbbell shape where it is aligned along the y direction. The red shows the direction of the y-axis, the blue shows the direction of the y-axis, and the red shows the direction of the negative y-axis. So it is a direction of the 2py dumbbell in 3D. So it means that the linear combination of the wave functions will also be the wave function of the hydrogen atom. But the linear combination of the wave functions will not be the wave function of the LZ operator. This is the plot of the 3p2, that is principal quantum number is 3, orbital quantum number is 2, magnetic quantum number is 0. So this gives you 3z square orbital 3z square orbital. And you know that in the 3z square orbital, as discussed in slide number 9, you can see that there are two lobes over here at the top and at the bottom, and there is a torus or the donut in the middle on the xy plane. This figure has been explained also in one of the previous slides. So you see that this will give you how the wave function, how the three-dimensional wave function of the hydrogen atom will take the form. That takes the maximum value, where these figures take the maximum values. The wave function will also be maximum there, and where these figures takes the minimum value, the wave function will also be minimum in this region. And the center of the nucleus is located where the center of the z-axis occurs. So let me go through some very important facts. The linear combination of psi are also the solutions of the Schrödinger equation with the energies given by equation number 41, but they are not the eigenfunction of the LZ operator. Energy levels corresponding to En, excluding n is equal to 1 for a given n, contains several different wave functions, and the levels are called degenerate levels. So you see that for a one value of n other than value of n is equal to 1, you have seen that we have different wave functions, that is different wave functions having the same value. And if some wave functions have the same values, such levels, such wave functions are called degenerate functions, and the corresponding energy levels are called degenerate levels. So degenerate levels mean that the levels correspond to different wave functions, but they have the same energies. So the degeneracy is typical of the hydrogen atom due to the central or the Coulomb potential. Since in the hydrogen atom we have the central potential, which we also call as the Coulomb potential, then the main cause of degeneracy occurs due to this central or the Coulomb potential. And the degeneracy again mean that there are many levels which are coincident with each other, with each other. That is, the levels are merging together, and the levels show that they have merged together, having the same energy, but those levels correspond to different wave functions. Such levels are called degenerate levels. The degeneracy with respect to orbital quantum number L is lifted, that is, energy level becomes dependent upon the value of L. If the potential no longer has the form minus constant over R, but still spherically symmetric. For example, in a hydrogen-like atom, the potential may be spherically symmetric, but it depends upon the value of, that is, the orbital angular momentum will not be zero for such atoms. Under such a condition, due to L being not equal to zero, the energy will be depending upon the value of L also. So the energy levels will be split with the values of L also. So we can say that the degeneracy may be lifted when the L is with respect to L, with respect to the value of L, which is non-zero. And also for the symmetric potentials, where for the atoms other than the hydrogen atoms, that is for the hydrogen-like atoms, where L may not be equal to zero. For all where L may take higher values. For all the atoms with more than one electron, their potential departs from the Coulomb potential. If the hydrogen problem is dealt relativistically, which is required for the exact treatment of spectra, the L degeneracy is also lifted. So you see that in the hydrogen atom, we have not used the relativistic treatment of the hydrogen atom. But if we have used that one, we would have noticed that the energy of the electrons will also depend upon the value of L. So the degeneracy is lifted when the subject is treated relativistically, where the L dependence also appear. Now the M degeneracy is also lifted by superimposing non-spherically symmetric potential on the central potential of the atom, that is by applying the electric field or the magnetic field. So you see that despite the fact that an atom has a spherical symmetric potential, even if you apply electric field or the magnetic field to such atoms externally, which means that you are making the atoms to depend their energy on the magnetic quantum number m, then of course the energy of the atom will also depend upon the magnetic quantum number m, and that is only possible when you apply the external electric or the external magnetic field. So you see that this was all about, and this is the end of slide number 10 of the course on atomic and molecular physics.